Welcome to Breadboarding. This is part 2 of video 43 of the Breadboard 8088 PC, and we're adding an IDE Hard Disk drive and controller to the project. This is our plan. Last time we covered the design of the IDE controller and talked a bit about all the background. In this video we're going to go in a little bit more detail about the design, look in detail at schematic, look at the logic rules and things we need for the programmable logic, and then we'll build it out. So we summarised the design from the last video. We're going to base it on the XT-IDE Rev 4 design, but we're going to swap out two of the latch chips with one of these 74LS 646 chips. This will just minimise the number of connections and things we need to make, and also a lot of the glue logic will be replaced by one programmable logic device. So we're going to configure things for Rev 1 compatibility for the moment. There's the jumper configuration to configure the board in a slightly faster mode, but we'll keep things running sort of slowly to start with, and then we're going to need to configure the XT-IDE BIOS for tiny mode, which means that we get a 4K chunk of code to combine with the rest of the BIOS in EPROM, and we're going to be building that on the defaults of port 300 and the various other defaults and things. We're going to need to reconfigure the current BIOS that we use that's currently in a 32K EPROM, and at the moment the BIOS starts at F800, and we're going to shuffle it up by 4K or 1000, and then we're going to be able to fit the first 4K as being the IDE BIOS. And we'll be looking at the 2.5-inch drive and the adapter in a minute. So first of all, let's take a look at the datasheet for the 74LS 646. So these are quite hard to come by. I had to get mine off of eBay. You can't buy these from sites like Mauser and RS Components anymore, unfortunately. They are quite interesting in that if you're familiar with the bidirectional buffer, the 245 chip, which is common in a lot of designs, the direction and the G-bar pins are common to those designs. So the direction, generally when direction is 1, then it goes from A to B. When it's low, it goes from B to A, and the outputs are only enabled when this G-bar goes low. Now what this chip also has is a couple of other inputs. So there's two clock inputs, so clock A, B and clock BA. These determine whether or not the data on the corresponding port is latched in the latches that are contained within the chip. Now this chip actually has latches on both sides, so it can have things on the A side and on the B side. And then the select AB and select BA, these determine whether or not the output on a given side is coming just from a pass-through, so it's just acting like a normal buffer, or whether or not the output is actually coming from the latched data. So these are sort of things that we need to consider in doing the design. The diagram here is actually probably easier to see what's going on. So this is the cell that you've got one of 8 channels. We've got the A input and the B output, and then we've got our enable signal, the direction, the 2 clocks and the 2 select signals. What we can see here is we've actually got 2 latches here, so 2 flip-flops, both clocked negatively, and the outputs are in fact inverted. So you can see there's an inverted output there, but also the input here is also inverted. So we've got an inverted output there, but in fact the gate at the end there is also inverted. So effectively these cancel out, and really what you can see here is this is a selection logic to determine whether or not we're taking the output from this flip-flop or latch here, or we're taking the output directly from the input here, and that is determined by these selection lines here. And whether we got the output hit either this side or this side is determined by the G-bar enable and also the direction. So depending on that, then either this side will be enabled or this side will be enabled, or neither side will be enabled. So this helps to make it a little bit clearer. So the only real confusion here is that we've got inverted outputs here and inverted output there, but the net effect of that is really sort of ands and ors, so it makes it fairly straightforward. So if we go back to the XT-IDE Rev 4 design, which we were looking at previously, and what we need to do is to codify the logic. Now the 646 chip we're just looking at is going to replace these 2 values here, and you can see here that there's kind of a load or a clock value here, and there's also an output enable. So these are some of the values that we're going to need to work out how to produce. And if we look down at the select logic here, we've got this chip here just provides a configurable chip select. Now we're going to use 300 hexadecimal, so we probably don't need such a configurable chip. We'll just configure one of our existing PLDs we've got for address decoding to do that. And what this decoder here does is decodes the A0, A1, A2 chip select. These outputs will only be enabled when we've actually got the A0, A1 and A2 are all 0 and the chip select is low as well. And then what this then does is decode the IO write, the IO read and the A3 address line. So this is in the compatibility mode, the default slow mode, which uses the A3 line. So this sort of determines whether it's 300 or 308 for the higher byte. And then it's rather confusingly decoded out here. So these outputs are normally high and they're active low, and then some of them are also inverted, and then these values are then going up to the latch thing. So to work out what was going on here, took a little bit of getting your mind around it, and then the values here and then a number of the values here are then just buffered straight off to the IDE controller. And we've also got here the CS1FX, CS3FX, or CS0 and CS1 as they can also be known as. And so these are just decoded on the basis of the IDE chip select and the A3 line. We won't worry too much about the high performance mode where effectively the A3 and A0 lines are reversed. So this is a spreadsheet I used to help decode this. So the 74LS138 decoding. So you can see here that the active low input is just connected straight to the chip select. A0 is active low, and these other two, the positive input into E3 is only true when the other two values A1 and A2 are 0. And then the other section here is showing where the inputs for the IO write, IO read and the A3 address line input are going into the decoder and which values are actually used. Now we know that IO write and IO read can't be both low together because we can't be reading and writing to an IO device at the same time, so we know that those two combinations are invalid. And when they're both 1, then basically nothing's happening, and then when each one is low, that's when we're either reading here or writing. And then depending on what the A3 line is doing, we're either considering doing the upper byte or the lower byte depending on the A3 line there. So U1 is the CPU reading from the IDE drive, and U2 is the CPU writing to the IDE drive. So this is U2 and is writing, so the data is coming in this side and is going out to the D8 to D15 there, and then the D8 to D15 is coming in the data side here and coming out this side. So I use this information here to determine how the logic conditions work. And if we look back at the animated diagrams I showed in the previous video, so in the read diagram, we can see that the read order, we read the lower byte first and then the upper byte. So when we read the lower byte, we set the direction to be 0. So this means we're going from this direction to the CPU. We also have the output enable on the buffer is low and is enabled, so we can read the least significant byte or the lower byte actually to the CPU. And actually at the same time, what we also do is to latch the value which is on the upper byte here on the IDE drive. And by using the clock BA, we actually latch the data on the B port to the A latches on here, but we don't actually output it this time. We only then output it once we read the 308 address, and then we actually enable the output. The output enable is enabled there, and then the actual data for the upper byte or most significant byte will then come out of the latch values there and onto the data bus. In a similar way for the write order is slightly different. We write the upper byte first and then the lower byte. So when we write the upper byte, then the clock AB will actually take the data on the bus and I'll actually put that in the B latch there, but we don't actually send anything to the drive at that point in time. And then when we write the lower byte to 300, what happens there is we do the output enable for this with the direction set to 1. So this means we're going from A to B. So the lower byte will be sent in real time out there, but also we're then going to enable the output for this with the direction going A to B. And so because we have the select AB set high or to 1, then this will be using the latched output. So the data will actually be going out to the IDE connector. So it took a little while to work through all of these conditions. It's a little bit tricky, but hopefully we'll have got it right, and now we're able to actually encode that into the PLD configuration rules. So the rules for this logic and the corresponding triggers and things there have now been encoded into the PLDs. We have a look at the schematic. So as said in the previous video, we've now added to the I/O decoder that we added for the real-time clock here. There was a few spare outputs, so we've now got a chip select IDE. So this will be for the port 300 to 30F. We also needed 2 buffered outputs for the I/O read and I/O write, and since there were inputs to this one, then in fact I'm just going to hook up those 2 outputs there, buffered outputs, to the IDE connector down here. So those are the only changes needed for that chip. And then this PLD here really is the one that has most of the logic for the IDE drive. So we have the chip select coming in there. We've got our bus A0 to A3, so this is just normal address bus. We also have the I/O read and I/O write, and then these inputs are not actually used. And the outputs we have are buffered address. So this is the buffered address lines for A0 to A2. We then have the CS1FX and CS3FX, so those are CS0 and CS1 in other terminology. Then we have the upper clock B to A and upper clock A to B, and then we have the upper output enable and the lower output enable. And if we go back to our original diagram here, so these really are the output enables and the clock values there. So that corresponds with those labels there. And then the buffer here is just based on the direction. So the direction rules we'll look at in a minute. And then the lower output enable, again, we've just based on here. So this chip is responsible for providing the CS outputs, buffering the lower address lines which are used by the IDE drive, and also handling the output enables and the clock signals for the various latches. And you can see here that the select AB and select BA, these are both set to high to 5 volts, so they're always going to be using the latched values. They're not going to be using the pass-through values. So let's take a look at the PLD rules. So I'll have a look at the I/O decoder first. So the only thing we've done on the I/O decoder, we've now added the IDE chip select, and we've added the buffered outputs for the I/O read and I/O write. So all we've done is added the output. We've just added these 3 outputs, and the IDE write is just a straight copy of the inputs. And because we're doing the active low exclamation mark on the pin mapping, then whenever we read in I/O read and I/O write, because the input pins have the exclamation mark, then that will convert it from active low to being true under normal logic, so positive logic. And then when we send it back out again, because we've got the exclamation mark on the IDE I/O write and I/O read, then in fact we can just map the 2 together. So it's something you need to be careful of. If you have active low signals, it's probably simpler to actually put the exclamation mark on the pin mapping. Then all you have to worry about is things being true in all of the logic rules. And then we've got here the rule for the IDE chip select. This makes use of the signal from the main decoder, which just tells us when the A12 to A19 lines are all 0. So this just means that we can ignore the higher address lines for the majority of our I/O devices. And then the rule here just defines the range of 300 to 30F. And then the majority of the rules then are in this IDE PLD. So you can see we've got our inputs on this side and the majority outputs there. There are a number of pins which aren't currently used. Again, we're using the positive logic, so we're inverting the IDE chip select as it comes in. So chip select IDE is true when selected. And you can also see that the CS1 FX and the CS3 FX, which can also be CS0 and CS1, are also converted to positive logic. Now I've used the terminology here rather than the CS0 and CS1 just because that's what the XT-IDE card uses and also the BIOS, so I figured it'd be less likely to cause confusion. And then we've got our upper byte clock B to A, upper byte clock A to B, and then the output enables for the upper and the lower chips. And finally the direction will be true or 1 for A to B, which is CPU to IDE, false or 0 for B to A. So we then got our address mappings. The chip select 1 and chip select 3 are relatively straightforward. They're just combining the IDE select with the A3 value. So when A3 is 0, we get 300. When A3 is 1, we get 308. So the only slight confusion here is that the original design for the XT-IDE just uses the bus IO read signal to determine the direction. So that means that by default it's normally set to the high value, so it's actually going from CPU to IDE drive, and only when the read signal goes active low. Now because we're using positive logic here, this is one of the areas where you do sometimes with the positive logic and the pins having the exclamation marks on the definition. In this particular case, if we look back at the diagram, you can see here that the direction A to B just comes straight from the bus IO read ISA, which is the inverted signal. The asterisk on these diagrams indicates that it's actually an inverted signal. Therefore, because we're actually dealing with the positive logic and the mappings here, we do need to include the exclamation mark here because this direction doesn't have an exclamation mark mapping there. So we just need to be a little careful on that. And then the output enables, we then can actually make use of the CS1 and CS3, and then we're only interested in when the address lines are 0. We're only interested then when the IO read or IO write are active. So under either of those situations, we need the outputs to be enabled. Then finally, the clock A to B is when we have the CS3, the address lines are 0 and we're writing. And then in fact for the other one, we actually only want to latch the upper byte on read is when we're actually selecting the output enable here. So in fact we can just make use of the value of this rule here, because when we're reading the lower byte, then in fact we can then clock the upper byte. So hopefully those pin rules will be sufficient. I suspect when we start testing it, we might need to tweak some of these, but hopefully that means that it will work first time. And if we have a look at the chip labels, I've actually modified the IO2 decoder, now includes the additional lines there, and then I've also done a chip label for the IDE PLD here, so those hopefully will mean that we're less likely to make mistakes wiring things up. So let's take a look at what the bits we're going to be using for making the disk controller. So here's the SATA drive connected to the SATA to IDE converter. So this is the StarTech one. I did have another one which didn't seem to work very well, so once I've got this working, I'm going to see if that other one will work as well. And then this will just plug into the Molex connector that I've been using for the floppy disk controller. Now in the NanoComp project, I created an IDE connector like this, and then it's just wired up to a standard IDE cable. Now one of the subscribers, Peter, very kindly has made a number of connectors and he sent them to me, and one of the connectors he's made, there's a floppy disk one which I'm already actually using for the, see here, this is one of Peter's floppy disk controller connector which I'm already using, and he's also kindly sent me an IDE one which is a little bit neater than the stripboard Breadboard one, so I'll be using that, so thanks very much Peter for that. I'll be adding another breadboard down the bottom of the layout here. You can't quite see it where the camera is at the moment. So we've got a breadboard buddy which is going to be doing the power rails between the other board. So where the real-time clock is, there's a little bit of space there. So hopefully I'll be laying out the, so that's our buffer, the 74LS245. This is our 646, difficult to come by, and this is the PLD that we'll be using. So there's not a lot of components, so hopefully shouldn't take too long to wire this up, and then we'll just need to worry about configuring the BIOS. Okay, so I've trimmed one of the power rails off this breadboard here, so it should actually fit up close to there, so I'll fit that in a minute. I've soldered the pins on the breadboard buddy, so this is like the power rail PCB that ties the boards together. I'm hack modular on Tindy. I've taken Peter's connector that he made for me, so this is an IDE PCB 40-pin IDE, and what I have done is I've put the labels of the pins on each side of there, so it makes it a bit easier to connect everything up. So we just need to make sure that there's enough gaps for everything to plug in, and I've also got a load of these DuPont cables where the 8-way connectors on the end. So I've shown previous videos where I make these, so you basically take the individual clips off and then put in one of these sort of shells. It makes everything a lot easier. So what we're going to be doing is feeding the data lines from here to here, then another data feed from there to over here. The output is going to the IDE on this side, the output the IDE on this side, so that will take care of all of the data bus side of things with a minimum of wiring, keep things simple. And then we've got various signals we've got to come from the address lines over to here, IO read and IO write coming over here, and then most of the signals here are coming over to here and to here. We've got the direction and the output enable need to come from here over to here, and then there's the control signals here. So most of the signals are going to be fairly local. So, and then we've also got some decoupling capacitors here that we'll need to put close to the ground rails on all of these chips, and perhaps we might also move our power meter, voltage meter down to the bottom board here just to show what the voltage is on this bottom rail here. So what I'm going to do now is just to speed this up, and I'll commentate over it just to let you know what's going on. So let's just replace the breadboard buddy, connect the two breadboards together, put in our breadboard buddy, make sure the chips are in. So I'm just going to hook up the ground and the plus 5 volt lines for all the chips and put in the decoupling capacitors close to the ground rails. Then we need to do all the IDE connector ties to ground, so it's quite a few ground connections, and there's also 1 or 2 pins we need to tie to ground as well. We'll just check those off on the schematic. So there's a couple of other things. We need to tie the 2 select A, B and BA inputs to 5 volts as well. So now we're doing the chip select IDE and the IO read and IO write bus signals. So now we need to wire in the A0 to A3 address lines which are coming in from the top right there. Okay, check those off. Now we're wiring in the direction for the 2 buffers and the output enable for the lower byte and the output enable for the upper one. Then the 2 clock signals for clock AB and clock BA. So now we're going to start to look at wiring up the address lines, the buffered address lines going to the IDE connector, and then the CS1FX and the CS3FX, which are the 2 sort of chip select lines for the IDE drive. Now I need to put in the LED for the drive activity, and there's a couple of pull-up resistors we need to put in there for some of the other control lines. Check those off. So now I need to do the buffered IO read and IO write, and then the reset connection from in there. Then we just need to wire up the data ports. So that's the input from the CPU data bus going to the top there. So that's the least significant lower byte, then the upper byte, and then the output from the lower byte to the IDE connector. So we're just then compiling the PLD files and programming them. Just speeded this up, so we've done this quite a few times, and then the other PLD. So both the PLDs now programmed. Okay, so we've finished plugging everything in. So we've got our voltmeter down the bottom here. So this is off the bottom power rail, just to make sure that we've got good voltages all over the place. So I've updated this PLD to version 3, which includes the chip select for the IDE and the buffered IO read and IO write. This PLD has been updated. We've just got to plug in the IDE cable. The IDE drive is actually sitting on top of the floppy disk drive that I showed you earlier, so just need to plug that in. Now, before we can use this, we still need to update the BIOS, so we need to add the XT-IDE BIOS extensions so that the BIOS can discover those at boot up. I think that's probably going to take a little while to do, so what I'm going to do is to break the video now, and in the next video we'll be sorting out the BIOS and hopefully being able to boot MS-DOS from the hard disk. So if you don't want to miss out on future videos, please hit subscribe. If you can hit like, it just helps to make the videos available to a wider number of people. Thanks for watching.